All right, lesson 3, acceleration. We talked about acceleration earlier last time we met. An object moving to the right with initial speed of 25 meters per second, right, suddenly feels a constant acceleration of 5 meters per second to the left. I think it's a good idea that we actually establish the directions so that we are all on the same page, okay? So let's consider direction to the right is positive direction, and to the left is the negative direction, okay? And then we're going to also consider up to be positive direction and down to be the negative direction. So we should establish that right off the bat, okay? So we're going to try to keep this convention unless you're told exactly what direction is what. So this can be safely assumed. So in our case, we have 25 meters per second to the right, right? To the right, 25 meters per second. That means this is the initial velocity. So V initial is positive 25 meters per second xat. We're going to assume that it's going to stay on the x-axis in one-dimensional motion. Then suddenly feels a constant acceleration of 5 meters per second squared to the left. All right, so here we have acceleration of, to the left, 5 meters per second squared xat. So write down the initial velocities and the acceleration. Boom, that's done. Part B. 3 seconds after the acceleration acts on the object, what is object's velocity? Well, first of all, what's happening to this object? If this thing is moving at 25 meters per second and then suddenly experiences negative 5 meters per second squared, right? What's going to happen to this? Somebody.
It'll go to the left 15 minutes. So
Well, is it going to, first of all, is it going to speed up or is it going to slow down?
it's gonna slow down.
It's going to slow down. It's going to slow down, right? It's going to slow down 5 meters per second every second as long as it's going to the right. But eventually, when it slows down, slows down, slows down, slows down, it's going to have to stop eventually at certain time. And then it's going to get pulled to the left 5 meters per second every second. So it's going to go to the right and slows down as it goes to the right. So good. So that's established. So here, 3 seconds after the acceleration acts on the object, what is the object's velocity? Well, we know that acceleration, by definition, is change in velocity over change in time, right? That is same as Vf minus Vi over t. So if I multiply both side by time, and then bring this negative Vi to the other side of the equal sign, make it positive, I can say Vf now is equal to Vi plus At. If you don't know how I got from here to here, come and see me after school and we'll have a nice heart-to-heart talk. All right? So now that we have this, we can use this equation. So we know 3 seconds after acceleration, so we know time is equal to 3 seconds. We know initial velocity is positive 25. We know acceleration is negative 5. So we have all the ingredients to find out my Vf. So my Vf is equal to initial velocity of 25 plus negative 5 times 3. So here we have 25 plus negative 15, and I have positive 10 meters per second. X hat is how fast it will be traveling after 3 seconds. So how many seconds does it take to come to a stop? Well, when it comes to a stop, we know my final velocity at that exact moment is 0. So utilizing the same equation that we have developed earlier, Vf is equal to Vi plus At, we're going to consider Vf to be 0. 0 is equal to Vi, which is 25 again, plus negative 5 times t. So if I bring this to the other side, it becomes negative 25. So negative 25 is equal to negative 5t. So time is equal to 5 seconds, right? 5 seconds when my velocity is 0. So it takes 5 seconds to stop this thing. So instantaneously, it stops, and then it changes direction and goes the other way. So now it's going negative direction after 5 seconds. Okay? So what is the velocity of the object, right, 2 seconds after it has stopped? So after it stopped, which is it takes 5 seconds to stop, and 2 seconds after that, so my time is 7 seconds. Okay? Therefore, again, Vf is equal to Vi plus At. Okay? My Vf is equal to what we're looking for. My Vi is 25 plus negative 5 times 7. So my final velocity in this case comes out to be 25 plus negative 35, which is negative 10 meters per second, x hat. If they were to ask for speed, it would be just 10 meters per second with no negative, no x hats. But since they wanted velocity, we have to give the direction. All right, any questions so far? All right. Now let's take a look at number 2. An object moving to the left, right, to the left, has initial speed of 5 meters per second. So my V initial is equal to, right, negative 5 meters per second x hat. Suddenly feels a constant acceleration of 10 meters per second. So my acceleration is 10 meters per second in the left direction, so negative 10 meters per second squared x hat. So what's going to happen to this object? What's happening? And what's the motion going to be like? Come on, somebody. Is it slowing down? Is it speeding up? Is it staying the same speed? What's going on? Come on, somebody shout it out. Speeding up. Good. Which way? In negative direction. Very good. So we'll use the same equation when time is 3 seconds, right? So they want to know what's going to happen when t is equal to 3 seconds. So here, when t is equal to 3 seconds, right, I want to know how fast it is going. What's the velocity? So my Vf, again, is equal to Vi plus At. my VF is equal to VI, which is -5 plus -10 times 3. So my final velocity after 3 seconds is equal to -35 meters per second xhat. All right. Now, an object passes. No. How many seconds does it take to come to a stop? Or does it stop? This will never stop. Right? It will go faster and faster, right? In the negative direction forever. All right, it'll just keep going faster and faster in the negative direction forever. All righty. Any questions so far? All right. Then, number 3, an object passes through the origin moving upward with initial speed of 50 meters per second. So an object, right, is moving through an origin. So this is the origin. So it was thrown from way down there probably, and then it was moving up. And as it passes through the origin, it was traveling at 50 meters per second upwards. So my initial velocity is equal to 50 meters per second y hat. All right, and it's positive 50 meters per second. And is acted on by downward acceleration, right? Downward acceleration of 10 meters per second squared. So acceleration happens to be -10 meters per second squared y hat. So how many seconds does it take for an object to come to a stop? So when this thing is going up at 50 meters per second, and is slowing down by 10 meters per second every second, how long will it take to stop instantaneously just for instant, and then starts to fall back down 10 meters per second every second, right? So you could predict that it's going to be 5 seconds, because 1 second later it'd be traveling at 40, 2 seconds later 30, 3 seconds later 20, 4 seconds later 10, 5 seconds later it probably stops instantaneously. Then it'll be -10, -20, -30, -40, and so on meters per second as time progresses. So how many seconds? Well, we could predict that it was 5 seconds, but let's see how it works out using the equation. So here my VF is equal to VI plus AT. Well, when it comes to a stop, my VF is 0. So my 0 is equal to VI, which is 50, positive 50, plus -10 times t. So -50 minus 10 is equal to -10t. So t is equal to 5 seconds. So we were correct. Now, what is the speed 8 seconds after it has stopped? So if it takes 5 seconds to stop, and then 8 seconds after it stops, the total time happens to be 13 seconds. So they want to know what the speed is. So VF is equal to VI plus AT. So VF is what we're looking for. VI is 50 plus negative 10 times 13 seconds. So my VF is equal to negative 130 plus 50 is 80, negative 80 meters per second, y hat. So that's my final velocity after 13 seconds. However, since they want the speed at 13 seconds is just 80 meters per second. No direction needed. All right, it's just 80 meters per second. All right. Any questions? All right, I hope that was easy for everybody, and I'm sure it was. Okay. So let's take a look at the next question. All right. So these are concept questions, and they're pretty, important. So, one, if one object has a greater speed than a second object, does the first necessarily have a greater acceleration? And the answer is, what would you say? If one object has greater speed than the second object, does the first necessarily have a greater acceleration? What would you say, Andy?
I would say no.
And I would say you're correct, right? I would say you're correct. And answer is no, definitely not, right? Because if you were to think about, let's think about your dad's Porsche, right? Porsche 911 Turbo, right? This is old classic model, right? So it only does about acceleration of 12 miles per hour per second. So it can accelerate 12 miles per hour per second. So every second, you can change your velocity 12 miles per hour, is what that means. And, right, it reaches, right, 60 miles per hour in 5 seconds. And it stays there, let's say. It only stays in first gear, right? And it stays at 60 miles per hour, right? But Honda Civic, right, can accelerate 8 miles per hour per every second, right? And reaches 80 miles per hour in 10 seconds. Well, it looks like Honda Civic has higher speed, but it takes 10 seconds to get there. Right? So the acceleration for Porsche is definitely greater, but it doesn't have the higher speed because it only stays at 60 miles per hour and it gets there in 5 seconds. Versus Honda Civic, it has higher speed going at 80 miles per hour in 10 seconds, but it only has acceleration for 8 miles per hour per second. So there it is. All right. All right. Number 2. Can an object have a northward velocity? Right? Can an object have a northward velocity and southward acceleration? Can that be possible? Simple question, yes or no. Can it be possible? Can it have northward velocity and have southward acceleration? And the answer is yeah. Yes, definitely yes. The answer is yes. What would happen to this object if this is true? I mean, it says yes. So what would happen to the object? Come on, someone explain it to me. What would happen to this object if it has northward velocity with southward acceleration? Andy? It slows down, yeah. Until eventually it's going to slow down to a stop, right? Then it's going to actually speed up going southwards, right? So it's going to slow down as long as it's going towards the north. Then it's going to stop eventually. Then it's going to actually speed up going south. So the object, right, will slow down, right, while going north, right? Then eventually will stop stop, right? And change directions to south and speed up going south. All right. So it's going to slow down, slow down, slow down, slow down, going north as it's going up north. And then eventually the object will stop instantaneously and then change its direction to south and speed up as it goes to south. So as soon as that happens, the velocity is no longer north anymore. Then the velocity becomes south and acceleration becomes south. But until this happens, we can have velocity going up north and acceleration going south. Okay? So maybe we can, understand that this is only after it stops and changes direction. All right, so number 3. Can the velocity of an object be negative when acceleration is positive? Well, that's easy, right? What about vice versa? Right? So that's like going this way, my velocity and my acceleration's this way, right? Or my acceleration is this way and my velocity is this way. And then the answer is obviously yes, right? Because we just talked about it, right? C number 2. Right? So whenever the direction of the velocity and acceleration are opposite of each other, it's going to slow down. It's going to slow down. The direction of acceleration usually does not give you the direction of motion. The direction of velocity gives you the direction of motion. All right? When the direction of acceleration and velocity, right, are in same direction, then it will speed up in that direction forever. All right? So let's take a look at the next problem. Give example where both velocity and accelerations are negative. So if we were to look at that, we could say the velocity is negative this way and acceleration is negative this way. Right? This can happen when you're backing out of the driveway. Right? You put it on reverse, you release the brakes, you pop the clutch, and you speed up backwards in your driveway, backing out. All right? So this happens when backing out of a driveway, right? Going faster, faster in reverse, right? All right. A second example would be, right? So this is like one example, I guess. Right? A second example could be your velocity can be negative and your acceleration also can be negative if you were to throw something downwards from a tall place or dropping something, okay? You can throw something down, okay? From a tall building. So if you throw something down from a tall building, it would have negative velocity. And since the acceleration caused by gravity will always make it accelerate towards downward direction, you would have negative acceleration as well as negative velocity. All right. All right. Number 5. Is it possible for an object to have a negative acceleration while increasing in speed? Now, don't forget, this is velocity. Now, this is speed. Can an object have negative acceleration while increasing in speed? And the answer is yes, Lulu, that's correct. Give me an example.
Like if it's if the again, wouldn't it just be if the car's reversing and it's like going?
Absolutely. That is correct. So C, so yes, definitely yes. Right? C number 4. That is absolutely correct. Because when speed is without direction, so as long as you're going reverse and speeding up, you are going in the negative direction. Right? So when an object, I guess, right, has negative acceleration, and it is going in negative direction, right? Then the object will increase, right, its speed in the negative direction. Boom. Number 6. This one's a good one. I wonder how many people would actually get this. Can an object be increasing in speed as its acceleration decreases? Well, if so, give an example. If not, explain. Andy.
I said yes, and it would only work if acceleration and speed were both going in the negative, negative direction.
Or both positive direction too, right? So they have to both go in the same direction basically. Acceleration and velocity. Give me an example then.
So, like if you were, like if you had like a car and it was just kind of like if it was driving forward and then, I guess if you were like reversing and the acceleration is going in a decreasing direction and you ended up like reversing fast enough that your speed starts to go faster.
Okay. I can see what you're saying. That's not wrong. That's correct. That's correct. Andrew Mason.
I was gonna say, like, if you're at a red light or something,
Uh-huh.
right when it turns green, you're probably accelerating
Right?
much faster than maybe 10 seconds later, but you're still speeding up.
Okay.
That's fast.
Okay. That happens a lot, right? That happens a lot because when you're at Lancaster Avenue and it turns green, you want to go from 0 to 60 and then like you want to like sort of not continuously go 0 to 60 and then keep going faster and faster because you'd be going 100 miles per hour through Wayne, and you know those Radnor cops, they're like really bad. So if you want to go like, faster but not as fast as before, so you're sort of like easing off on your accelerator, but you're still going faster, is what Andrew is saying. All right, that's good. That's good. Will, do you have a example?
Yeah, I was thinking like a ball. You throw it up, it starts to start at a certain point, but it starts to go down faster and faster.
Ah, okay. I guess that can happen. That can happen, but that gets a little bit more complex. That gets a little bit more complex. So, I actually like both Andy's idea, right? Like, let's say you're like going faster, but you are actually not going as faster than this constant rate that we've been going. So let's say you're going, you're accelerating in your dad's Porsche 911 Turbo, right? So you're going like, 12 miles per hour and then 24 miles per hour and then like 36 miles per hour. And then you don't want to go as 12 miles per hour every second. So you sort of like ease on your accelerator, right? So you could sort of say like, well, answer is yes, obviously. That can happen. So you could go from like 0 to like, 12 miles per hour, right? And then to 24 miles per hour, and then to 36 miles per hour. But now, instead of continuously going at 12, 12, right? 12, 12, 12, now you are going, let's say you're sort of easing on your pedal, You're easing on your pedal, and now you're going only, let's say, 46 miles per hour, and then now you're going, uh, let's say, 54 or 52 miles per hour, and now to like 60 miles per hour, and so on. So like you're sort of like easing down. Instead of 12, now it's 10, right? Now is from here to here is like, what is that, 6, right? And then maybe I should do 58 or 56. Now we were doing 4, right? So between here to here is 12, 12, 12. Then here we're doing 10. Here we're doing like 8. And here we're doing 4. So now it's still increasing speed, but the acceleration is actually decreasing. Where this is constant acceleration of 12, but now you're decreasing your acceleration to 10. Now you're decreasing it to 8. Now you're decreasing your acceleration to 4. So the speed is still increasing, but your acceleration is actually decreasing. Does that make sense for everybody? All right. So yeah, so that can definitely happen. So miles per hour per second, right? Miles per hour per second, miles per hour per second. And then this would be like miles per hour per second, miles per hour per second. So every second, the miles per hour actually increases, but the rate of the increase decreases. Now, this one's kind of tricky, huh? But this happens every day when you're driving, believe it or not. You just don't realize it. As soon as you let off on your accelerator, you are actually decreasing your acceleration, but you're still going faster and faster. All right, number 7. As a freely falling body speeds up, what is happening to its acceleration due to gravity? Right? Does it increase? Does it decrease? Or does it stays the same? Anybody have an answer for this one besides 2 Andys and Will? Come on. Come on. Camellia, what would you say?
I said it increases.
Acceleration due to gravity increases? Well, that could only happen if the Earth itself has greater mass, if the mass increases, right? This acceleration due to gravity only happens because of Earth gravitation. And Earth gravitation is pretty constant because the mass doesn't change. Andy, what you have a question?
No, actually, wait, I'm not allowed to. Sorry.
No, go ahead. You could answer.
Sorry, okay. Sorry. I had written down, I just want to make sure it's right, like a constant acceleration, but then you're increasing speed and velocity.
Correct. That is correct. So the acceleration caused by gravity is constant because Earth gravity is constant, right? And gravity for now, I mean, until we get to like later on when we get into like relativity and stuff, it's caused by the mass. Like more massive it is, more gravitational pull it possesses, right? But like some people would say like, yo, but Mr. Kim, isn't Earth getting like heavier? And I'm like, what do you mean heavier? Well, I guess like cosmic dust and asteroids and I guess meteors can hit Earth. I guess it could technically get like slightly heavier, but it'd be so negligible because they're really small, amounts. And somebody said, but what about all those like buildings and like those highways that we build? Aren't they making it heavier by building all those buildings? And I said, well, where do we get all those materials to build those buildings from? It's like from the ground. So are we making it heavier? It's like, oh, you know. So the mass itself for the Earth is really not getting more and more massive. So because of that, the gravity will stay constant. And if gravity stays constant, that means our acceleration due to gravity will stay constant. All right. So the acceleration due to gravity remains the same, or simply constant, right? Right? Because the gravity of the Earth stays constant. Okay? This makes all objects, right? And when I say all, I mean everything, right? Right? Near the surface of the Earth right? Accelerate at 9.8 meters per second every second towards the center of the Earth. Because if we say down, I mean, what about the people in Australia? Their down is our up, right? So it's really towards the center of the Earth, because their down should be for everyone on Earth. It should be towards the center of the Earth. Will, you have
Wouldn't wait, wouldn't gravity increase when they really far away? The like the Earth's gravity from the near the moon, because
yeah, as you further and further and further go out of the surface of the planet, the gravity of the Earth will change, correct? Because the distance is so far away. But as long as you are close to the near the surface of the Earth, inside, our atmosphere, you really don't lose that much of gravity. Like for example, tallest place that we can think of that we can actually reach as humans is Mount Everest, right? That's like 5 miles above the sea level. And when we actually do experiments there, even though it's five miles above the sea level, acceleration due to gravity is only like 1% difference. So it's really not that much of a difference. So even if you're way out there let's say out in the atmosphere and above the atmosphere, and then you go you know orbiting around the Earth at like 25, 30 meters above the surface, it would still be gravity, and gravity will be there, and it's probably going to be about like 96% to 98% of our gravity. Because if that gravity wasn't there, we would not be orbiting. I hope that answers your question, Will.
makes
Yeah. All right. All right. Any other questions before we move on? All right.